And that's, I think, something that you've already seen in, I think it was in Bernard's lecture, where classically, so people used to be interested mainly in this quantity itself. And why is this quantity interesting? Because it allows to bound this. And also because it allows to tell something about algorithm in general. So this was for the empirical risk minimizer, but for any algorithm that takes its functions in a class G, you can do the same thing and show that difference between the loss of the algorithm and the loss of the best in the class is less than some quantity here. That was the quantity that was less than 0 for the empirical risk minimizer, and the supremum here. So, okay, if you look at it this way, it's not very interesting because most often, so what you would do here, because you don't know what this function is, you would drop this term. And if you drop this term, you obtain something here that may not converge to 0. The empirical error of your classifier may not converge to 0 if you have some noise, for example, or whereas this goes to 0 and this may still go to 0. So that's why this kind of analysis would not be used directly in if you don't have the empirical risk minimizer. Instead, you would do something like this. You would just look at the loss of your algorithm, but not compare it to the best in the class. And so this is true for any classifier. The loss of your classifier is less than the empirical loss plus the supremum, right? And that's, again, why you consider this supremum. Okay, so what we had here was a factor of 2. You can actually remove this factor of 2. This is a slight refinement. You do the same inequality. It's exactly the same inequality, but you take the supremum only for upper bounding this quantity. But you leave this quantity like this because that's a fixed function. G sub G is a fixed function, so you know that you can control this easily via Hofding's inequality. Okay, so you keep this term here. And in particular, when you take the expectations, this term vanishes because, again, it's a fixed function. So you get rid of the factor of 2. Okay, so now we come to what I call the union bound. And that's the key ingredient in going from inequalities for individual random variables or fixed functions to inequalities for many different random variables or suprema of random variables. Okay, so let's take the simplest example, simplest case. We have two functions, for example, in our class, and we consider the set of training samples for which the difference between the true and empirical average of one function, say the function I, is larger than some value. Okay? So for each function, we look at all the bad samples, all the training samples for which this function does not look like it should on this sample. Okay? And what we have seen before was that with Hofding's inequality, the mass, the probability mass of the set, or the probability that your sample is in the set, is less than some delta, where delta is related to epsilon in a certain way, right? Epsilon is essentially square root of log 1 over delta over n. So we have this inequality for each of the set, and now what we want to bound is the probability that the sample is bad simultaneously for two functions, right? So which is the probability that the sample is it has to be bad for either of the functions. So if it's bad for one function, then we can be misled by this function. If it's bad for the other one, we can be misled by the other function. So we want to bound the probability that the sample, the training sample, is bad for one or the other, right? So which is the union of C1 and C2. And okay, we have seen this inequality before. Probability of the union is less than the probability of the individual events. Okay, so what you obtain, and directly generalizes to more than one function, we can get the sum. So what we obtain is that the probability that there exists a function among our sets, here we consider finite sets of functions, such that for this function the difference between true and empirical is large, is less than the sum of the deviation for all individual functions, where we have seen with Hoeffding's inequality that this is less than exponential minus twice sample size epsilon squared. Okay, so the additional factor we have is this n here. So the probability is multiplied by n. So now if we go, if we do this inversion trick, so instead of talking about probabilities, we fixed the confidence level and go back to the values of the deviation. It tells us this thing here. If we fix the level delta, then simultaneously for all functions in this set, we can ensure with high probability that the difference between the true and empirical loss will be less than same thing as before, square root log 1 over delta twice n, plus an additional factor which comes from taking the log of the previous inequality here. And that gives us the log of the cardinal of our class. Okay, so and now this inequality is true simultaneously for all g. So it in the picture we had before, where is my? Okay, in the picture of the empirical process, what we had before, okay, assuming we have finitely many functions here, we know that if we look at a fixed function, we have 1 over square root of n deviations. And if we look at simultaneously all the functions, the maximum deviation that we can find anywhere here on this set will be of order square root of log n, log capital N over small n. Okay, so it will be larger by a factor which is logarithmic in the size of the set of functions. And this is very important because it ensures that you can have quite a lot of functions. Still, this quantity will first go to 0 with the same rate, 1 over square root of n. And the size of the class of function only enters logarithmically. Okay, and of course, using these fundamental inequalities relating the maximum regret to the supremum over the class of the deviations, you obtain that the maximum regret for the empirical risk minimizer is less than twice this quantity with high probability at least 1 minus delta. Okay, and the nice thing is that this result here does not depend at all on the distribution apart from the distribution being IID. So we can say, in some sense, that when we have this class G, and we want to compare the performance of our algorithm to the best in this class, using the empirical risk minimizer, so just picking the function in this class that performs best on the training data, will give an algorithm that does almost as well as picking the best in the class. So we match the performance of the best function. Okay, so let's summarize things. What we have shown is that in this IID framework, if we look at a fixed function, the deviations are of order 1 over square root of n. If we have capital N functions, the maximum deviation in the class are of order square root log n over n. And this is a very common phenomenon. And essentially, you can keep this in mind as a rule of thumb. When you have one random variable that has some deviations, okay, the random variable has to have exponential tails, which is the case for many random variables. But if you consider several such random variables simultaneously, the maximum value of these random variables will behave as log n times the behavior of the individual random variables. So if you, I mean, you can imagine doing this in layers. So for example, you have now several classes of functions. You have capital G1, capital G2, and so on. You have several algorithms. One algorithm picks its function in G1. The other algorithm picks its function in G2, and so on. And you look, you're interested in the best function, a best classifier among all these classifiers. Then you would get an additional factor of log number of such classifiers, right? So if you want to enlarge your class by saying, okay, maybe I take one classifier is a decision tree, and one classifier is a linear classifier. I have bounds for both of them. If I take the best of them, then what I lose in my bounds is a factor of log 2. So it's not much, in a way. And it also tells you how to trade sample size with size of the classifier. So if you lose this factor of log 2, it means to get the same performance, if you want, you need to have an increase of the sample size that is equivalent to this factor. So it tells you how to trade sample size with complexity, or at least complexity as measured by the cardinality of the classes. Now, it happens that we can improve quite significantly these results. So first thing was, as we said before, that this Hovding's inequality may be loose in certain cases. Right? In particular, we used only the fact that the variable is bounded, but we did not use other properties of the random variables, for example, the variance. And with this, you can already improve a little bit this inequality. Second and most important point is that when we did this union bound, we did not care about what the functions were. We just knew that we had capital N functions. No matter what they are, we said we just upper bound by the sum over all probabilities, and we got this factor log n. Okay? And another direction into which you can improve this kind of result is when you look at this quantity, it's a bit crude to upper bound. Remember, the supremum was coming from upper bounding this difference, which was the difference obtained for the function returned by our algorithm, and we replaced that by the worst difference in the class. But maybe this does not always attain the worst difference. So by using this fact, we can get also refined bounds. But our main objective will be to refine the union bounds here. Okay. It happens that for refining the union bound, we first have to introduce the other refinement I was mentioning, the refinement on the deviations. So let's come back to what our random variables look like. This empirical average of the loss is what is called a binomial random variable. And what does it mean? It means that it's a sum of random variables that can have value 0 or 1. And there are n of them. And they have value 1 with probability small p, which is exactly the probability of error, the probability that we make an error. Okay? So we know completely the distribution, at least in this special case where we have binary classification, we know completely the distribution of this random variable. And we can actually compute exactly, we can have an equality here, the deviations of our random variable of interest, again for a fixed function here. And it's equal to this quantity here. It essentially tells you that you have these n examples. You have 0 or 1 for each example. You have 0 with probability 1 minus p and 1 with probability p. So if you have k ones, this happens with probability p to the k, 1 minus p to the n minus k. And there are n choose k ways to have k ones among n examples, right? And you do the sum for all values such that the sum of the ones divided by n is is larger than t, which is why we have this term here. Okay. Now, okay, this is not always very convenient to work with. So there are a bunch of possible approximations, or actually there are upper bounds on this quantity that simplify it. The simplest one is Hoeffding's inequality. And the important thing here is that it does not depend on the value of p. So it's independent on the distribution, which is nice in certain cases, but which can be a bit loose in other cases when we have information about this. Now if we go back this way, actually Bernstein inequality is already taking into account the variance, because actually small p is the expectation of the random variable, and small p times 1 minus p is the variance of the random variable of interest. Okay, so actually in this special case again with binary random variables, it doesn't matter really whether you talk about expectation or variance, because they are more or less related directly. Okay, and then there are more refined bounds, but which are a bit less easy to work with. So we'll concentrate on this or this. Okay. So if we look at Bernstein's inequality, for example, we see that for small t's, this will be small here. So we will have a term which is more or less of the same type as Hoeffding, which is e to the minus t squared, which is typical of tails of Gaussian random variables. Yes?
Are those inequalities useful if you have to estimate p from data?
You mean small p from data?
Right, because...
Yes, yes. You can, well, it seems that p, you need to know p to apply these inequalities, but we'll see that there is a trick to actually use this for estimating p. So for small t, this behaves like a Gaussian tail, like Hoeffding. For large t, this term becomes dominant, and we have e to the minus constant times t, which means exponential tails like Poisson random variables, for example. So, I mean, if everything were Gaussian, it would be simpler, but it's not the case, unfortunately. So that's what is said here. We have Gaussian behavior where the variance of the Gaussian is more or less the variance of the random variable. I mean, the tail of a Gaussian is exactly e to the minus t squared divided by twice the variance. That's a standard upper bound on the tail of a Gaussian variable. So this is exactly the same as if we had the Gaussian variable with variance p, 1 minus p. But in addition to that, we have also this heavy tail behavior. Okay? And the maximum, the worst case, if you want, for this quantity is when the variance is maximized, and the variance is maximized when you take p equals a half, which means this is 1/4 times 2, 1/2, which gives Hoeffding's. Okay, this is just to illustrate this fact. So here, this step function here is the cumulative distribution function of the binomial tails, the binomial random variable. So this is the exact computation with this sum that I showed before. Okay, and these are the upper bounds, the various upper bounds, Bernstein, Bennett. What is this? Binomial tail is the one that we had. No, it's the exponential, what I call exponential here. And the best Gaussian is like ignoring the extra term in Bernstein's inequality, so it's like just using this. Okay? And this is done for the worst case variance, p equals a half. So for p equals a half, more or less, they all behave the same. I mean, you don't see a big difference. Well, you notice that it's quite It's significantly different from the step function itself, especially when you are at the in these regions here. You are very far from the value of the upper bound. But actually, if you were to increase the sample size, you would notice that this step function becomes closer and closer to these exponentials. So at least it captures the right rate. Now, if you have a small variance, the pictures looks different, and in particular, the upper bounds that take into account the variance are much sharper than those that do not take into account the variance. Okay, and here you see the heavy tail behavior. Like here, I have drawn this curve. Here is the best Gaussian tail. So it's like ignoring one term in the Bernstein's inequality, and you see that for large deviations, so this is a zoom of this graph, right? For in this region here. So for large deviations, the tail is no longer Gaussian because you cross this Gaussian upper bound, and it's better captured, or at least it's upper bounded by the other quantities. Okay. So how do we use these inequalities in a meaningful way? So first thing, to simplify, we can keep the whole thing, but to simplify, we just replace the variance by the expectation, which in this case is an upper bound on the variance. Right? In general, it may not matter very much because the functions we are interested in have small error, and since they have small error, this is more or less like 1. So we don't lose much by doing this. Okay, and if we use Bernstein's inequality and do this inversion again, same thing. So instead of working with probabilities, we work with deviations. We get something like this. So there are terms that are familiar. The square root of log 1 over delta over n, that's something we already had with Hövding. But comes in the variance, or the upper bound on the variance here, which means the smaller the variance, the smaller this term. And we have an extra term that comes from this heavy tail behavior, which is actually not very important because as the sample size increases, the weight of this term becomes negligible compared to the weight of this term. Okay, so in a way, this is also reminding you of this central limit theorem. Like in the end, if you sum up enough independent random variables, you will obtain always a Gaussian behavior. So in a way, this you can see it here. This will disappear when n becomes large. The main term will be this one, which comes from this Gaussian e to the minus t squared behavior. Okay. So we can ignore essentially this term and just remember that the fact that we use the variance adds this term to the main contribution here. So of course we can combine this with the union bound again. So apply the same trick, write this for all individual functions in our class, and sum up for a finite set of such functions. And what we would obtain is same factor as before. We have this extra log n factor that comes in. Well, here I have put them together for gaining some space, but this is just log n plus log 1 over delta. Right? And same here, but again, I said we ignore this. So essentially, we have the same as before, but the additional term is that we have the loss. Of course, this is not really usable as this because we don't know this quantity. Right? And this is true simultaneously for all g. So now the trick is to, I mean, it's more or less algebra. You use this inequality here. The fact that if something is bounded by something else plus square root of this something, you can kind of solve this. This is like a second degree polynomial equation. You can solve this equation and show that when this is true, then this is true. You put all the a's on the left, and then you have this. So you essentially replace the square root of A by square root of B. And in our case, A is the true loss, B is the empirical loss. So with this trick, you flip the true loss and the empirical loss, and you obtain a bound where what comes in the square root is the empirical loss. Okay, and from this you can estimate from the data with a better estimate as before the true probability of error.
So who obtained this kind of bound for the first time?
That's a good question. Well, the first time I saw it was from, the oldest reference I have for it is in Vapnik and Chevron-Enkis, but
they used this also.
sorry?
They used this also.
Yeah. But I don't know if it's. I guess Bernstein would have add something like this for one function. Okay, so again, just keep in mind this term. Visualize it. You have empirical error that dampens the term. So the smallest the empirical or the true error, the smallest the deviations, and the largest the class, the largest the deviations. So in particular, if you take a very special case where you don't have any noise, where the target function, the true function, belongs to your class, then first of all, the loss of this best function is 0, no noise. And in addition, the empirical risk minimizer always makes 0 error. You can always find a function that has 0 empirical error, which means is this in this bound that this term will vanish completely. Right? This will be 0. Get rid of this, and you only remaining term is this one, which actually is much smaller. So again, that's something to keep in mind. In this ideal case where you don't have noise, convergence may occur much faster at rate 1 over n instead of rate square root of 1 over n. So you need much less sample to get the same accuracy in your estimate. And of course, you can have all intermediate rates depending on how the noise behaves, and depending on certain conditions, can show that you can have anything between 1 over n and 1 over square root of n. You can have 1 over n to some power between 1 and a half. Okay? So, are there any questions so far on these deviation things? Okay, so now the thing is, of course, this helps us obtaining slightly better deviation bounds. So we have already improved our bound to some extent by introducing this factor in the square root. But the important thing is that, in addition, this property of random variables having smaller deviations when they have a small variance will help us decrease significantly this factor here, the log n factor. And that's where we can improve really what was called the union bound. So to improve the union bound, there are two ways. And it's very important to understand the distinction between those two approaches. I guess we will treat this one now and this one this afternoon. So the first one is kind of a trivial modification of what we have seen so far. It's to introduce weights on the functions. So how do we do that? So remember that we had something of this form. The deviation is the probability that the deviation is larger than square root of log 1 over delta over n, smaller than delta. And we can write this for each function f in our class. And in particular, nothing prevents us from choosing a delta that is different for all these f's. Okay? So if we write these inequalities for all the f's in our class, and then go to the supremum, or the version where we say the disjunction of all these events, which is the fact that there exists a function for which this is true. Then, again, union bound, we can sum up all these deltas. So before we always have the same delta, so here we ended up with n times delta. But here, what we will do is to take a delta that depends on f in the sense that it's some delta, some fixed value delta, times a weight, small p of f, where the weights are actually a probability distribution on the class of function. So we have, say, n functions, and instead of putting a weight uniform, 1 over n, 1 over capital N on the function, we can take any other weighting. We can distribute the mass as we wish on the class of function, such a way that this sum to 1. And when we do that, of course, since this sum to 1, here we have delta. And when we do the, when we write it in the standard, or in the same way as before, what we obtain is that with high probability, for all the functions in our class, true error is less than empirical error, plus same term as before, but where the log capital N is replaced by log 1 over the weight of this function. So now this bound itself depends on the function, so which makes it a bit less easy to use, but you can say that since this is true simultaneously for all functions, if you happen to have a classifier that returns you a function which adds a very small weight, a very large weight. So this is a bit surprising because if you have, say, n function in the class, what I said before is that the worst deviation is log n, log capital N. But now what I say is that if you change, and this is just a mathematical trick, it has nothing to do with how the sample behaves. But if you change the way you weight the functions, then you may very well have a very small bound for certain functions and a very large one for other functions. And of course, the best bound that you would obtain is Hovding. But you can have anything between Hovding and the log capital N, or even worse if you have a small weight on the functions. So in a way, you can just arrange such that the fluctuations will be, because you know that for a fixed function the fluctuations are of order 1 over square root of n, you can distribute your weight such that simultaneously for all functions there will be functions for which the deviation is 1 over square root of n, or small quantity divided by square root of n, and for other the deviation will be large quantity divided by square root of n. So it's a bit surprising, this phenomenon, and the point is, of course, you are not allowed to cheat, which means you are not allowed to choose p before you see the data, right? You have to choose this p independently on the training sample, otherwise this mechanism doesn't work. So which means that you have not seen the data yet, it's just a bet. You would bet that maybe the function is more, the target function is more of this type or more of this type, and you can say, well, I bet a lot on this function, I bet a little less on this function. And if your bet was correct, so if it happens that the function on which you put the most bet has a low empirical error, and your algorithm chooses this function, then you will have a very good bound for this function. Okay, so this is the consequence of this approach is that, okay, first you can get a better bound if you are lucky, in a way. And second thing is also it allows to extend the union bound to the infinite case, because in the infinite case you can do the same thing and put weights that decrease on all the functions, or at least in the countable case. And then it's you will have a bound for the countable case. Okay, so I'll stop here and we'll continue this afternoon. Any question? Yes?
Related then to like a prior user?
Well, you can of course think of it as a prior because it's a distribution on your functions. So nothing prevents us from saying, well, if I have an algorithm that uses as a prior a certain p, I can put this prior in the bound and get a bound that depends on this prior. But you can also take another prior, different one from the one that is implemented by your algorithm. And the puzzling thing in a way here is that you can get arbitrary bounds if you vary this prior. So the question is, what is the p that we should put in here to get the best bound in a way? And well, the best p is the best bet you can have on which the function should be. So even if your algorithm implements a certain prior, you may have a different belief in what, I mean, you can have a Gaussian process prior, for example, and still believe that the function that you will obtain has certain properties and that you did not put in your prior. And if you know certain properties in advance, then you can put them in your bound prior. So yeah, ideally, the most information you have, the better the bound you obtain.
So suppose you really use your true prior, you put in all the knowledge that you have, and then you do a complete Bayesian inference to find the function that, or the distribution over function that you're going to use. Is there some statement that you could say that then the right prior is the one that you should put into the bound?
Yes, I think so. If you believe that the functions that your algorithm will return or will pick.
If it picks a single function. So if you, I mean, it wouldn't work for Bayesian averaging, right?
Well, okay, there are tricks to make it work also for Bayesian averaging, but okay, if your algorithm picks a single function, then and it picks this function with a certain prior, then this is the prior you should put here. And actually, it allows you, for example, if you knew in advance that your algorithm is a bit stupid, for example, it has a large class of functions to pick from, but it always picks the same one, no matter what data you give it. Then you can put a large weight 1 on this function and 0 on the other ones, and you recover everything bound. And you can, like this, if you know that most likely the algorithm will return functions in a small region of your space, then you should put more weight on this and get a better bound as a result.